Hello everyone, welcome back to Geology 01A at West Valley College. I'm your professor, Professor Farida Baksamusa, and today we'll be studying sedimentary rocks. Sedimentary rocks are the foundation of much Earth's surface geology and one of the richest sources of information we have about Earth's history. By the end of this session, you'll be able to identify sediment types and grain sizes, explain how sediments are transported and deposited, understand how loose sediment becomes solid rock, recognize major groups of sedimentary rocks, link sedimentary structures to past environments. So let's dive right in, pun intended. So what are sediments? Sediment is just loose material, particles of rock or mineral that have been broken down through weathering. We studied weathering in the previous lecture, and it's moved by water, wind, ice, or gravity. Now, sediments are classified primarily by their grain size. Gravel is granules, pebbles, cobbles, boulders larger than 2 millimeters. Okay. Sand is from 2 millimeters down to 0.063 millimeters. You can see the grains and it feels gritty in your fingers. Silt, on the other hand, too small to see individually. It feels smooth in your fingers but gritty in your mouth. Clay, the finest grain size, smooth even in your mouth. So quick thought exercise. So when you go to a local beach or riverbank, what do you feel? Sand, pebbles, rounded cobbles. This instantly tells us about the energy of the environment. Strong waves versus calm water. Sediments don't just stay put. They're transported by moving water, wind, and even glaciers. Here's the key principle. The faster the flow, the larger the particles it can carry. A raging river in floods can move boulders. A quiet stream, on the other hand, only moves silt and clay, and even then slowly. There are important ways sediments move in rivers. Traction, large class sliding or rolling along the bottom. Saltation, medium grains like sand bouncing along the bed. Suspension, fine silt and clay carried within the water column. Solution, ions dissolved invisibly in the water. Here's a fascinating fact. A clay grain may remain suspended for long so that it can travel across entire ocean basins before finally settling. Sediments accumulate in particular depositional environments. These include streams forming gravel bars, sand layers, or mud in quiet backwaters. Lakes, often fine-grained clays and silts. Deserts, wind-blown sands form vast dune deposits. Glaciers drop mixtures of clay, silt, and boulders all at once called till. Marine settings, deltas, beaches, reefs, lagoons, and deep-sea muds. Each environment leaves its own signature in the sediment, later allowing geologists to read the rock record and reconstruct ancient landscapes. Loose grains don't automatically become rock. They must undergo lithification, literally turning to stone. Now, two steps are crucial: compaction and cementation. Compaction is overlying weight squeezes grains together, pushing out the water and air. Cementation, dissolved minerals such as calcite, quartz, and hematite precipitate in pore spaces and bind grains together. The result? Sedimentary rocks that may last hundreds of millions of years. Now, sedimentary rocks fall into two main categories: clastic and chemical, including biochemical. What are clastic rocks? They are made of broken fragments. Mud rocks, dominated by clay and silt, if laminated shale, if massive mudstone. Sandstone, quartz sandstone, arkose, feldspar-rich, lithic vaccae, rock fragments. Conglomerates, coarse, rounded class transported far. Precious, coarse, angular class deposited near source areas. Coal, organic fragments often grouped with clastics. Chemical or biochemical rocks, formed from dissolved ions. Limestone, mostly calcium carbonate, often formed from reef organisms. Dolestone, altered limestone with added magnesium. Chert, fine silica from radiolarians and diatoms. Evaporites, salts like halite, gypsum, or sylvite formed when water evaporates. Banded iron formations, ancient deposits of iron oxides tied to Earth's oxygen history. Remember, the mineral content of the rock often reflects both the environment and the chemistry of Earth at the time of deposition. Sedimentary rocks don't just tell us about grains, they preserve structures that give clues to past conditions. For example, bedding, layers of sediments accumulated. Cross-bedding, angled layers from dunes or ripples showing flow direction. Graded bedding, coarse to fine grains common in submarine fans. Ripple marks, preserved wave or current action. Mud cracks, wetlands dried up recording seasonal climate. Imbrication, class tilted by stream flow. These small-scale structures are like snapshots of ancient rivers, deserts or seafloor. For sediments to survive long enough to lithify, they need basins, areas where they can accumulate and be preserved. These are often controlled by plate tectonics. Trench basins next to subduction zones. Forearc basins between trenches and volcanic arcs. Foreland basins adjacent to large mountain ranges. Rift basins where continents stretch apart. Geologists classify these deposits into formations and groups. Distinctive mappable rock units and groups are collections of related formations. Members and beds, smaller divisions when detail is needed. This system gives geologists a common language for mapping Earth's layers and correlating rocks across regions. Finally, fossils. Though we won't cover them in depth here, fossils in sedimentary rocks are vital. They help to date the rocks, the faunal succession, reconstruct paleo environments, marine versus terrestrial, shallow versus deep, infer climate, temperature, and even ancient ocean chemistry. For example, foraminifera shells in deep sea mud can reveal Earth's average temperatures for the past 65 million years. To help geologists study and communicate about layered sedimentary sequences, rocks are systematically organized into groups, formations, and members. These are more than just words. They intentionally recognize units that help us map, describe, and compare rocks across the world. Formations are the basic building blocks, a sequence of beds distinct enough in appearance and composition to be mapped as a unit. Groups are collections of related formations often deposited in a single geologic basin over millions of years. Members are subdivisions within a formation defined if there's a practical need to distinguish thinner units such as ski, coal seams, or sandstone beds. Now, naming. These units are almost always named after the area where they're found. For example, the Nanaimo group. Let's bring these ideas to life with a real-world case. The Upper Cretaceous Nanaimo group on Vancouver Island, the Gulf Islands, and the parts of Vancouver area. During the late Cretaceous, about 90 to 65 million years ago, thick sequences of sediment conglomerates, sandstone, mudstone, and coal accumulated in the foreland basins between present-day Vancouver Island and the mainland. This enormous series is called the Nanaimo group, which stacks up to 5,000 meters thick. The Nanaimo group is divided into 11 formations, each defined by significant changes in rock type, which reflect dramatic shifts in ancient environments. Some formations record quiet marine conditions, others fast rivers or swampy deltas ripe for coal formation, and some the deep turbid submarine fans. Here's a sampling of these formations and their environments. The Gabriola Formation, submarine fan sandstones, high energy. Spray Formation, fine grained submarine fan mudstones. Pendant Protection Formations, river delta sandstone, minor coal, transitional from marine to river. Tension and Comox Formations, near shore conglomerate sandstones and coal, reflecting ancient floodplains, swamps, and beaches. As is standard, these formations are always presented with the youngest at the top and oldest at the base. In coal mining regions near Nanaimo, additional subdivisions called members and even named beds were created for key coal seams and rock layers of economic importance. So next time you see a name like Comox Formation or Gabriello Formation on a geologic map, realize you're reading a page in the record of Earth's ancient environments, classed and named so we can reconstruct the basin's history, correlate rocks regionally, and even target resources like coal. Let's bring everything together now. Today, we explored how sediments, loose particles like sand, silt, and clay are formed, transported and deposited in a variety of environments from rivers and beaches to the deep sea. We saw how, through the processes of compaction and cementation, these sediments can eventually become solid sedimentary rocks such as mudstone, sandstone, conglomerate, and even coal or limestone. Each rock tells a story about the forces and conditions of its environment millions of years ago. We looked at the fascinating structures preserved in these rocks, like cross bedding, graded bedding, ripple marks, and mud cracks, each providing clues to ancient landscapes and processes. We also learned how fossils can reveal the age and environment of deposition, unlocking secrets about Earth's past life and climate. And finally, we discussed how geologists organize these layers into groups, formation, and members, often named for the place where they are found. The Nanaimo group on Vancouver Island stands as a great case study, a 5,000-meter thick record of ever-changing rivers, deltas, swamps, and submarine fans divided into formations and members to help us map and understand the region's geologic history. So in summary, sediments and sedimentary rocks aren't just simple layers. They are the pages of Earth's diary, recording everything from ancient floods and deserts to tropical reefs and life's evolution. Understanding how we classify and interpret them lets us uncover the stories of our planet's deep past. Thank you so much for joining this journey through sediments and sedimentary rocks. And if you have any questions, please come join my Zoom link, or send me an email on Canvas, or send me a text message and I can help you. I can set up a Zoom with you. And good luck with your study questions and your lecture questions. And I'll see you in the next video. Bye-bye.